In this lecture, we will learn about another important relationship that the components of strain have to satisfy. So, this arises from the fact that we are assuming that we have cases at hand, or the problems that we are going to solve are going to lead to single valued displacements which vary slowly over space, which means that suppose I know the displacements at point O. So I know the displacements here. This is the displacement vector at O. And if I want to find the displacement vector at a neighboring point P, which I called UP, then this is kind of what I'm going to do. To get UIP, I start with UIO, which I know, and then I traverse along some path C, and as I traverse along the path, I pick up these small displacement increments, these small increments in the displacement, and keep adding them as I traverse the path. Now I can easily write this DUI in this form. What I have done here is I have just used the fact that DUI is equal to del UI dx1 plus del UI dx2 plus del UI dx3, which is simply the chain rule. I have used that. Here I am emphasizing the fact that this integral here over the path C can be thought of in terms of the derivatives of the displacement, that is ui comma j, and therefore from the strain displacement relation, which is like epsilon ij equal to ui comma j plus uj comma I, because of the strain displacement relation, these gradients of displacement are actually connected to the strain. So I can actually think of a problem where I want to find the components of the displacement at P, knowing the components of the displacement at O, using the strains, that is integrating the strains over a particular path C. Now, since this path C is nothing special, if I take another path to go from O to P, if I take another path to go from O to P, I should actually get the same result of this integration, because my displacements are single valued. I do not expect to encounter any cracks or discontinuities along any of these paths. Any path is exactly similar to any other, and therefore this integration should be basically path independent. So if I use the strains to get the displacements at a point, knowing the displacements at a neighboring point, then I should be guaranteed of single valued results, no matter which path I choose. Now, this is not automatically going to happen, because there are 6 strain components and there are only 3 displacement components, and it turns out that the strains have to satisfy additional conditions between themselves. The strain components have to satisfy additional relationships among themselves in order to make this happen, in order that we have some chance of making this happen. So what we want is the relationship between the components of strain such that when I integrate them, I get single value displacements. The proof of this is there, that these relations are called compatibility relations for strain. The proof is there in the next two and a half slides. I'm not going to go through the proof because the proof is rather long and not very relevant for our purposes. I'll fast forward to the final result, and the final result is this. So this is the condition that the strains must satisfy. This is the conditions that the strains must satisfy, strain components must satisfy among themselves, in order that when I integrate them, I get single valued displacements, and these conditions are called compatibility relations. Now you will see that I, J, K, L all are free indices, and therefore there are 4 of them, so there are 81 such equations. But fortunately, out of these 81, most are actually repeats of each other. You can imagine that roughly, because when I write epsilon ij uh, comma kl, I know that this is equal to epsilon ji comma kl, because this symmetry is guaranteed by the fact that epsilon ij is epsilon itself is a symmetric tensor. But this also means that del square epsilon ij del xk del xl, it means this, which for continuous functions epsilon ij, in our case everything is continuous, there are no discontinuities anywhere, this is same as for continuous functions this, which means that this will also be equal to E ij comma Lk. So there are symmetries with respect to KL, there is symmetry with respect to Ij, and all these symmetries taken together will lead to the fact that out of these 81 equations, only 6 survive. Only 6 equations survive, and these equations are given here. So these are the equations that form the general set of compatibility relations. So these are the compatibility conditions. For the strains, all of them involve second order derivatives of strains on both sides, and if these are satisfied, then we can integrate the strains in order to get single valued displacements. Now I will take up a problem and I will try to show the problem will be kind of an anticlimax. So I'll try to show that this is not a sufficient condition, and there can be situations when we get kind of counterintuitive, we can have counterintuitive kind of results. They're not so common, but I know of at least one where there's a paradox, and I will highlight that. But you must remember that compatibility conditions are need to be checked for all solutions that we are going to do later in this course. Compatibility conditions are kind of sacrosanct, though they are not sufficient conditions for single valuedness of the displacement. So I am going to show you an example next where we will see that it's not sufficient, but it is a necessary condition. It is a necessary condition that needs to be checked for all solutions in situations where you are planning to get the displacement field by integrating the strain field. When you are planning to get the displacement field, there are some problems in the problem set that ask you to do that. When in those situations, you need to check for compatibility. Okay. So let us take a displacement field, which is a well-known displacement field. This is given by U1 and U2 are 0 everywhere. So these two components of displacement is 0 everywhere. And then U3 is given by some constant B divided by 2 pi, and then tan inverse of x2 by x1. So for any point given here, what I have plotted in this figure, for any point I can calculate the U3 by taking tan inverse x2 by x1, and that's what I have done in this plot. And from this plot you can see that there's a jump in the displacement when I cross over this axis. When I go in this direction, when I cross the 0 here, there is clearly a jump in x3, x1, x2, u1, u2 are of course 0. There's a jump in u3. There's a jump in u3 when you cross over what I have labeled, I think, as the x1 axis. So as you cross over the x1 axis, you have a jump in the displacement. Now, clearly the displacements are discontinuous. And now what I'm going to show you is I can take these displacements and I can calculate the strains. So I can calculate the strains, for example, 1 strains 1, 3, which would be half of del u3 del x1 plus del u1 del x3. So this is 1, 3. I can also calculate 2, 3, which will be half of del u3 del x2 plus del u2 del x3. However, this is 0 everywhere, this is 0 everywhere, and therefore I have only this term to calculate. I have the functional relation. I can easily calculate this derivative and this derivative and get epsilon 1, 3 and epsilon 2, 3. So then I am going to go back to my compatibility relations. These are the 6 compatibility relations where I have one equation. I have one equation which involves 1, 3 here. I have that same equation involving 2, 3 as well. Other equations don't involve 1, 3 or 2, 3. So other equations are identically satisfied. This is the only equation that I need to satisfy. For example, this is identically satisfied. This is identically satisfied. And because epsilon 2, 3 is not a function of x3, epsilon 3, 1 is not a function of x3, these are identically satisfied. This one is not identically satisfied, but I will show you that if we do the calculations, if we do these calculations, if we calculate epsilon 3, 1, so all I have done is del u3 del x1, half of that, that's this, and this is half of del u3 del x2. This is what I have calculated, and then I put it in this fourth compatibility equation here. I put it in this fourth compatibility equation, the only one that is not trivially satisfied. So I put it in, and then I see that it satisfies the fourth compatibility equation. But I had started with a displacement field that was clearly not continuous. So it is possible to have a discontinuous displacement field give you compatible strains. It is possible for that. This actually is a well-known displacement field that arises around a screw dislocation. So I guess you have done material science courses and you know what screw dislocations are. This is a displacement field that arises around a screw dislocation, and this displacement field, it's well known that it satisfies the compatibility equation. The strains that arise from it satisfy the compatibility equation, though the displacements are not continuous. The displacement field is not continuous. This shows that probably the compatibility equations are not sufficient for single valuedness of displacement. However, they are necessary, as I said, and they are important equations that you need to remember. We will see in 2D cases. In 2D cases, actually out of the 6, in most 2D cases, the first equation only has to be satisfied. Everything else is identically satisfied. When we are working in the 1-2 plane, you can see that all these equations are trivially satisfied, and only one is left, and that is the one we will have to work with when we are doing 2D problems. This completes our discussion, theoretical discussion on strain. We will change gears a bit and look at how to see strains. So how strains are measured and how measured strains are interpreted. Dr. Venkatanaran is going to take over from now on for the next 3 or 4 lectures. The next quiz is going to be on the theoretical part of strain that we have completed today, and then the next to next quiz, which will be a longer quiz, which will not be a half-an-hour quiz, which will probably be a day-long quiz, which will be taken by Professor Venkatanaran on the experimental part, which he is going to explain to you next. Okay, let's stop here.